Session. My name is Royce Floyd. I'm an associate professor at the University of Oklahoma. I'm also the associate director of the Southern Plains Transportation Center. And I'm really excited to get to moderate this session because it's about all of my favorite things, including concrete, bridges, bridge repair, and pavements. So we have four exciting presentations for you all in this session. And so let's go ahead and get started with our first speaker, Dr. Tyler Lay. Is a professor of structural engineering at Oklahoma State University. He's going to be talking to us today about a pooled fund study on integrating construction practices and weather into freeze-thaw specifications. Dr. Lay has more than 20 years of experience in structural and concrete materials engineering at a lot of different places, many years at Oklahoma State University, where he does a lot of exciting research. He's won a lot of awards. I will say that you can read all the bios of the presenters in the programs, but Dr. Lay is also very involved in the American Concrete Institute, and as was mentioned earlier, he has a very exciting YouTube channel all about concrete, and he's had educational materials there viewed more than 6 million times. He could probably tell you the actual number if you wanted to know. But without further ado, let me introduce Dr. Tyler Lay.
We'll try to take this mobile, keep going. The slides ready? Look at that. Up, pow. It was working earlier, but now, Micah, it's not. Oh my goodness gracious. I need some help, my friend. Please. Okay. It doesn't go backwards. It doesn't work at all. It doesn't work. Let's see here. Maybe I got to get closer to him. The green means on, doesn't it? It's like there's a ghost in the machine here, ladies and gentlemen. Okay, it seems to be working now. We'll see for how long. Hey, thank you so much for being here. Thank you for having me. Man, we'll just do this on the floor. How's that sound? That way I can come and see you, look in your eyes, and see who's sleeping and who's not, right? Just like class, all right? So we'll get started, and good luck, cameraman, catching up with me. All right, so a big thanks to everyone that's on the slides today. I could not have done this work without it. And I want to tell you up front that this is actually one of the most challenging projects I have ever worked on in my entire life. This is something I dreamt of working on when I was a graduate student. So graduate students, your dreams can come true. Yes, even more than just graduating, right? You can dream things and make things happen. So let's get started here. Big thanks. So I'm going to ask a question, and I need you to help me out here. I need you to respond to this, all right? So I'm going to ask a question. Would you do the following? Would you spend 0.5% more on your project to double the life? Now think about that for a second. And we're going to answer. All answer together. 1, 2, 3. Good. I'm glad you answered that. Okay? Now, if I talk about the first plank, that's about what would we need to do to make something happen. And this concept is what research is all about, really. That I can spend small amounts of money and have huge impact, right? And what do we need to do is the very first question. And the second question is to double the life. What is the impact that we're going to ultimately have? And that every single presentation today is going to boil down to these two things. What do we need to do? And what impact can we have? And I'm going to come back to this in the end for my project, but I would challenge you every single time to think about what this means for you, what this is for you, what this is all about. So I'm going to acknowledge all of these states up here on the slide. This is a pooled fund study. So this Oklahoma led it. Big thanks to Oklahoma for leading it. But all of these states contributed money to help solve these big problems, all right? And I'll talk about one big problem today. We worked on many of them, so I'm going to do my best to smash 5 years of research in about 18 minutes. And so that's another thing. I'm not sure I can do that or not, but we'll see. But massive thanks to Gary Hook and Ron Kerb for making that. Let's give them a round of applause for all they do. Seriously, making this happen. Big thanks for that. Let's get started. So why is this research important? What is this all about? What's going on here? Well, if I have concrete, right, and if that concrete gets wet, if water starts to sit there, and if that concrete becomes saturated, becomes really, really wet, and then it subsequently freezes, then it can become damaged, okay? It's damaged by the freezing event itself. That's not good. And you're like, I don't understand. Well, water, when it goes from a liquid to a solid, there's a 9% volume change, right? And you're like, I still don't understand. So I did an experiment for you, just for you. Last night, well, actually, it was yesterday evening in my fridge. I took a can of Coca-Cola, right? And I put that in a freezer. Yep, put that in a freezer, right? It was sealed just to see what would happen. Don't tell my wife because I haven't cleaned it up yet. Yeah, I know she's not happy with me at all. This is what happens. 9% volume change, ladies and gentlemen, causes an explosion, goes all over, makes a great picture. It's going to be a great YouTube video. Okay, but not necessarily making your wife happy. And it's not necessarily good for your concrete as well. Because if this happens in your concrete, it can become damaged. It can cause things to have a problem. If that makes sense, do you give me a yes on 3? 1, 2, 3. Oh, good, you're awake. So how in the world do you design for freeze-thaw events? How do you do this right now? How does this work? Well, first the question you ask is, will the concrete freeze? That's the first question. And if the answer is yes, then you put something called an air entraining admixture in the concrete. This is like a soap that stabilizes bubbles inside the concrete. You have to get enough air, 6% plus or minus 1% air volume. And if the answer is no, you put no volume, no air entrainer in it at all. No, you add no extra air. And you might say, I could ask you the question. I'd say, hey, does this make sense to you? And some of you might say yes. And I would say, this is nonsensical. This is the stupidest thing I've ever seen in my entire life. You're like, I don't understand, Tyler. Well, weather is not the same everywhere. Does everyone agree with that? Freezing is a little bit different places. Moisture content's a little bit different places. Don't you think that could have an impact on this phenomenon? I think it could have an impact on the phenomenon, right? This, if you're still not with me, if I said, hey, how would you design a road for traffic? And if I did the same thing that I did for air entraining concrete, and the first thing I asked question is, will there be cars? And if the answer was yes, I build I-35. And if the answer is no, I build a hike and bike trail. Does everyone see how this is illogical? Give me a yes on 3. 1, 2, 3. Oh, they're not. The left-hand side gets it. The right-hand side is not so sure. There must be not traffic engineers over there, right? Does everyone see that it's kind of silly to design a one-thing-fits-all category? This binary decision. Freezes, yes, add air. Same amount no matter what. Doesn't matter where it is. It's illogical. Doesn't make any sense. But we do this because we don't know how many damaging freeze-thaw cycles there are. We don't know how many freeze-thaw. No one's ever quantified it. No one's ever done it. So you're like, damaging freeze-thaw cycles. What's that? Well, the Halloween's coming. Yeah. You excited? I'm excited, right? Kind of scary time, right? And what matters is that freezing only damages concrete when it's critically saturated. That means when the degree of saturation is above 80% inside the concrete. You're like, what? What does that mean? Well, degree of saturation, that's the percentage of water that fills the pores. So if I'm at 100%, I'm like totally saturated. If I'm at 0, I have like no water inside of it. So high DOS means it's wet concrete. Low DOS means it's dry concrete. You with me? Oh, good. You gave me a yes. I didn't even ask for it. I appreciate that. So what does this mean? This means if my degree of saturation, if my moisture content of my concrete is below 80%, the concrete will still freeze, but it doesn't cause any damage. Think about like back to the Coca-Cola I showed you before. If the Coca-Cola can is only half full when it freezes, do you see that that's not going to explode all over your fridge? But when it gets very, very close to the top, that 9% volume change, that causes all the damage. Same thing happens in our concrete. Exact same thing. We just have to understand where these places are. And when freezing event happens, you're like, man, that sounds impossible. Yeah, it's hard. It's actually one of the hardest projects I've ever done in my entire life. Okay, but I'll tell you how we did it. But in summary, if the concrete's dry when it freezes, it's not going to be damaged. But if it's wet, that's when it does. So how many of these happen every year? Or this year compared to next year, compared to last year? Sounds impossible. We need to know inside of the concrete what the moisture content is, the degree of saturation. We need to know the temperature in the concrete. And we need to know and see ice forming inside the concrete. Oh my gosh, what's going on? How would we ever do this? Well, let's start out. On the left, we have a form that's filled up with concrete. And there's some sensors in there. And I'll talk about those sensors coming up. They're stainless steel rods. Very easy. You can see all the wires coming out. I also have temperature sensors. I'll talk more about those coming up. We actually encapsulate those in concrete. That thing right there is encapsulated in concrete. The only concrete around the outside's only job is to protect the wires and insulate it as well. Just protect the wires. But those inner concrete, that sunken area, that's done on purpose. That's done to simulate a poor drainage area on a pavement, on a bridge, something like that. So when it rains, the water doesn't leave easily. It stays there. Why? Because it's the worst case scenario. You know those places exist on your roads. You know those places exist on your bridge. Those places that don't drain, that's your enemy. And that's what I'm trying to simulate with these tests. So we've got these hooked up to these weather boxes where we can measure how these things change over time, right? And there's actually one here. Baha, the great Baha, right over there, wave your hand, Baha, is over there telling and showing one of these weather boxes if you want to come see it next door. It's amazing. You should go see it. Inside of it, here's the cartoon. Every half inch, we have one of these stainless steel rod sets. We also have temperature sensors. Yeah, temperature sensors. So we can measure the temperature inside over the depth and the air temperature of the concrete as well. Now, between those stainless steel rods, we actually send electrical signals. And we can measure the moisture content of the concrete, and we can see ice forming. You're like, what? How is that possible? Well, when concrete is wet, it's easy to send an electrical signal from one to the other. When concrete is dry, it's hard to send an electrical signal from one to the other. And when ice forms, it's wet, so you're sending signal, and all of a sudden the solid ice particles make it really hard to send signal. So when it gets really easy, then really hard to send signal, ice just formed. And you also have temperature, so you can see ice forming. It's pretty crazy. It's pretty awesome. We put it in 42 different locations in the United States. So we measured this for 4 years, the data in the field. So this helped us measure the number of damaging freeze-thaw cycles that actually happen in real life. So instead of just talking about what's going on, we went out and measured what's truly happening. And this is a map from one of the years. And let's zoom in on this area right there so we can see what's going on. So I'm just showing Oklahoma because we're here in Oklahoma. We got some visitors from Kansas. We got some Arkansas. Hey, Arkansas didn't pay, so you're not on there, okay? So first number, freeze-thaw cycles. That's how many freeze-thaw cycles that we measured in Stillwater, Oklahoma in that year. Second number is how many damaging freeze-thaw cycles we measured. Remember damaging ones? That's when it's got to be wet. It's got to explode like the Coca-Cola inside your fridge. But now let's look next to it. What in the world is happening here? What was the first number? What was the first number? Number of freeze-thaw cycles. What's the second number? 0? 0? Has anyone ever been to Western Oklahoma? Everyone? We got some Western Oklahoma people. Yeah, we people out there. If you go to Western Oklahoma, right, and you walk out there, it looks just like this. Right, and tumbleweeds. I've seen more tumbleweeds than ever in the world in Western Oklahoma, okay? It's dry, ladies and gentlemen. It's the high desert. And in the high desert, it's so dry that it freezes, but it's not wet enough to cause damage from freeze-thaw cycles. And this didn't just happen in Oklahoma. These are 4 separate independent measurements. Does everyone see that? 4 separate independent measurements, all saying we're getting tons and tons and tons of freeze-thaw cycles, but no ice forming to cause damage. That's crazy. So what's going on over here? Look, look, look. What's the first number? Freeze-thaw cycles. Second number, damaging. See how it's a little bit lower? So this means that these are what I call kind of wet. That's an official term now. Kind of wet. Not super saturated, just wet enough sometimes to cause some problems. So in summary, we have dry, we have wet, and then we have my favorite kind of wet, environments. These all have the same latitude, or sorry, the same longitude, but because of different latitudes, they have different moisture contents. Does that make sense what I'm saying? So they have different amounts of damaging that's happening. This is really, really mind-blowing stuff. Yeah, I said mind-blowing stuff that's going on here, right? When we saw this is what we thought. We were like, oh my God, this is like happening. This is crazy. Then we asked another question. What weather causes these different DOSs? This is cool to measure it, but what weather is responsible for making these different DOSs happen? And we went into the soil literature. Okay, tons of soil literature about moisture contents and models to predict, because farmers really care about the moisture content inside their soils. And these are the 6 things that came up again and again and again in the soil literature for being really, really important to predict moisture content. So we're going to use those exact same things. And we wanted to use those to predict DOS, all of these things. So let me get this straight. I got tons and tons of weather data from many years. And I'm going to use all of this crazy data to predict one thing, what the moisture content is. What tool should I use to do that? Oh, baby, AI. This is perfect for AI. This is what AI is made to do. So that's what we did. We used machine learning models to do this. We used genetic algorithms to do this. We used our average monthly weather data to predict our average monthly DOS. Basically, if I know the weather, I'm probably going to be able to predict how wet the concrete's going to be. Does that make sense what I'm saying? And the weather did that. We correlated the air temperature to concrete temperature. We determined region-specific thresholds for our different models. What does that mean? That means the weather's different in different parts of the United States. That's probably not too surprising to you. But there's a little bit different tweak to the model you have to make for each one of these different regions. Different amounts made bigger differences. So this genetic algorithm, we trained the algorithm for 1 year of data, then we compared it to 3 years of measurements. We had 4 total. 1 year of training, 3 years of actual stuff that we compared it to. We accurately predicted our DOS more than 90% of the time. That's insane. I think that's insane. We could accurately predict our freeze-thaw cycles more than 95% accuracy. That's craziness. Isn't that good? She thinks it's good. Do you think it's good? I think it's good, right? So what does this mean? This means that you can accurately predict the number of damaging freeze-thaw cycles by only using weather. That means I don't need the blocks anymore. The blocks were cool. They're amazing. But I only need the weather to be able to predict all this performance. That's super powerful. So, well, okay, that's fine. You say this is powerful. How can we use this? What can we do with this? Well, we took 574 weather locations, over 24 years worth of data for each one. We combined them, we made interpolation algorithms to look at values between stations to get the best values. We made maps that look like this. Usually you see this in like, oh, what's the temperature going to be today? What's the high going to be today? We can tell you how many damaging freeze-thaw cycles there's going to be on average based on 24 years worth of data. This is powerful. You can look in different regions and start to make decisions about where do I want to entrain my air and where do I not want to entrain my air. This is like getting the key information that we've been needing from our understanding of what's been going on. But then we built an online tool because maps are cool. I think they're really cool. But these online tool, it's free, it's simple, and it's already out there. And all you do is you put your latitude and longitude in for your project. You hit a button, and it will tell you how many freeze-thaw cycles, how many damaging freeze-thaw cycles, and the variation, how much it varies from year to year. It's pretty powerful. So like this is for Denver, Colorado. Put in the latitude and longitude, hit a button. It tells you how many damaging freeze-thaw cycles, how many normal freeze-thaw cycles, and what the variability is. It helps you to design, helps you think about these things. So what's next? Well, the next step is to give guidance, is to actually tell people and say, this is how much air you need in this location. This is how much air you need in this location. We're working on that now. We want to extend that to the missing states. I don't really feel comfortable giving advice about how many freeze-thaw cycles there's going to be in a state if I haven't taken measurements in that state. Does that make sense what I'm saying? Right? So you really need to be able to measure in places like Arkansas, because that way you could give them guidance, right? And maybe we could extend this to other types of concrete, different water to cement ratios, vertical concrete, all kinds of other things as well. This is a start, not an end, but it's something we've never had before. And it's been my dream for more than a decade to get work on something like this. And this was the hardest project I think I've ever worked on in my entire life, okay, to bring all this stuff together. So I told you I was going to talk about these two things at the very beginning, and I'm going to talk about them now, and I'm going to give a very Oklahoma-specific slant. So what do we need to do? We need to tweak our freeze-thaw specs for local combinations of moisture and freezing. And I've given some of that. So there's some places on Earth right now that we don't use enough air entrainment inside of our concrete. And there's some places on Earth right now, like Oklahoma, where we use too much air entrainment inside of our concrete. So Oklahoma, we're going to need to reduce, we have the possibility, the opportunity to reduce our air content, especially in western Oklahoma, but I think other places as well. What will this impact be? This could provide the correct freeze-thaw protection for the location. There are places that have been under-designed, but Oklahoma, we're not one of those places. This could help us reduce cement content, lower our concrete mixture costs, less hassle with air-entrained concrete. And air-entrained concrete, although I love it, no one else does because it's a pain to get right, okay? It's crazy. So in conclusion, field measurements have been made to determine the amount of damaging freeze-thaw cycles. Did it in 42 different locations over 4 years. A genetic algorithm's been used to predict freeze-thaw performance based on weather data to tie them together. We have maps and online tools that make this easy to show the average and the variation of the damaging freeze-thaw tools, and we're moving ahead with that. Hey, I do have this YouTube channel. Like, subscribe, leave me a comment sometime, right? I'm over 13 million views now, 122,000 subscribers. Thank you so much. Happy Halloween. I don't know what you're going as, but I'm going to be a Jedi, okay? Any questions? No, you can clap. It's okay to clap. Come on now.
Wonderful presentation, Tyler.
Thanks.
One question that I edit one journal. We have about 800 to 900 submissions, and we are seeing that the modeling papers, like similar to what you said, is increasing at a very rapid rate. So in your case, you said that the prediction is more than 90%. So in terms of the data that you use, that these models are pretty good, when you have enough data to train and validate your model, how do you know that you have enough data? And what would you need to do to have better confidence in the predictability? Thank you.
Great question. Would you be okay if I tweaked the question slightly? Okay. Okay. So what I heard was, it seems like we got good results. How do you know how much data you need? And how do you get maybe even more confident about what's going on? Those are the three questions, and I love it. A professor asked 3 questions in one. He's good at that. So the short answer is we did things on purpose to make it easier for our model to give us something useful. I didn't have time to talk about those today. For example, when it came to the DOS, we used 3 categories, okay? I'm a simple guy. I know traffic lights. We do traffic lights all the time in what we do. Low, medium, and high. If I'm only trying to reach 3 categories, it's much, much easier than doing a predictive model that hits every single category. Does that make sense what I'm saying? But for this problem, I don't really need to know the difference between 91 and 96. It's not different to me. So by doing that, I can use a lot less data to train my model. The other thing is that you got to use a lot of different models. We used, I think, 10 different models that we tried, because you have to figure out which one has the best shot. You're like, I don't understand, that seems like you're cheating. Well, every one of these machine learning models has a different specialty. And sometimes they call it the texture of the data. It's like the shape of the data. If you understand what the shape of the data is like, then one model has a better probability to work over another. But we tried 10 different ones. We found the one that was most promising, and then we made it better from there. We used 1 year of data to train and 3 years of data to test. That's really good, to only train on 25% of your data. Most people do the opposite. Most people train on 75% and they only predict on 25. But we set our model up to only predict 3 things: low, medium, and high. And if you're a researcher in this room, I think you should think very heavily about doing that. Because if you only get the simple problem right, but it still works, it's still good enough, it's much easier to do that and train on that. Now, you ask finally, how do you get more confidence? More data, my friend. That's why we got to convince Arkansas to come in, all right? I mean, but more data would help see what's going on. The other thing that we see is we see changes in weather, which makes sense. Over 24-year periods, we see like changes, like where things are happening. And so until you measure a true 24-year period, then how do you know if you can predict a 24-year period? But if we don't start measuring and predicting now, we're never going to get better. If we don't start using these tools now, we're never going to get better. But the last thing I'd say is I would never, ever only trust a machine learning model, ever. Whatever it predicts, it's like, it's an idea. It's a possibility. And then you test that, and you see. So Oklahoma, if you want to change your spec, I'd suggest you put some blocks outside with low air contents and see what happens. You probably already have some structures with low air contents out there, and you probably already know what happens. All the old ones have no air content. Right, before 1949, we didn't put air and train concrete. Well, 1936, we didn't put air and train concrete at all out there. So there's some data out there.
Thanks, Tyler.
Thanks.
So we need to go on to our next speakers. If you have questions for Tyler, we may have some time at the end. Find him during the break. Go see his demo. It's really exciting stuff. Our next presentation, we have 2 speakers. We have Dr. David Darwin and Mr. Walt Peters. So if they could make their way to the front. Dr. David Darwin is the Dean Akers Distinguished Professor of Civil, Environmental, and Architectural Engineering in the University of Kansas. He does research in a lot of different areas. He's a past president of ACI and a distinguished member of ASCE. Mr. Walt Peters has worked for ODOT for 52 years, primarily in the bridge division. He primarily works in bridge research, bridge inspection, and specifications these days. And he is married to his wife, Rita, and they have 3 children and 6 grandchildren. Walt knows probably more about bridges in Oklahoma than any of the rest of us ever will. So join me in welcoming our speakers, Dr. Darwin and Walt Peters.
Hey, good morning, everyone. So this presentation is going to be about some materials that we've been looking at that are designed to stop corrosion. And so we're going to look at a magnesium cement, My name's Dr. Walt Peters, or just Walt Peters, and with me is Dr. Darwin, who did the research at the University of Kansas. Point it towards. Okay. All right. So this is an outline of the presentation. We're going to talk a little bit about Mount Concrete, a little bit about the objectives of the study, research, summary, and future work. So, magnesium aluminum liquid phosphate is known as MALP. It's, I'm going to get a little closer, used to repair concrete, so that concrete can be a column, it could be a bridge header on a bridge deck, it could be a pre-stressed beam. Bruce Arnold over here is doing a project that we're repairing some fire damage on a pre-stressed beam, and we're using this mount material. So it's really statewide. We've only used it about 12, 13 different bridges that I'm aware of. It's what I'm looking to do is we built a lot of bridges in the 60s and 70s. I'm looking for a way to stop corrosion, that we have a deterioration rate that's 0, which is rather aggressive goal, but that's kind of what I'm aimed at. So this consists of magnesium oxide, calcinated aluminum silicates, graded aggregate and fibers, and liquid phosphate activator. Okay, Dr. Darwin started his testing about 3 years ago, almost exactly. And he's been looking at this material for some time now. And he's done some really good testing. We've learned an awful lot. We're looking at freeze-thaw damage, like Dr. Lay just talked about a great deal. We don't want materials that are going to have a lot of problem with that. And salt scaling, he's looked into that pretty hard. And he's looked at the mount material with an additive. And the additive that we're dealing with is from a soybean product. It's kind of a pore blocker, and it's called Endure. So he's doing the testing with and without Endure, and he's going to look at more than one magnesium cement. But what are the benefits of this mount material? It provides for rapid repair, gains high strength in an hour, and minimizes the time of a bridge closure. That mount material can be applied in very, very cold weather. It has this liquid activator, which is unique. Drawbacks: generates a lot of heat, and it sets up rapidly. Well, that's an understatement. It sets up rapidly too quickly. And we've had some locations where it's froze on us before we can actually get the material on there. So there's some alternatives. We're looking at another kind of magnesium cement. We'll just, for short, call it MKP, but magnesium potassium phosphate. This is water activated, so we got to avoid the cooler weather. It doesn't have the corrosion properties that the mount material has, but it is easier to work with. There's less heat that you're dealing with, and so it's easier to finish, which is a good thing in many respects. And it's, he says for vertical and horizontal, well, for vertical surfaces and overhead surfaces, they put a little V, it says VO. Well, that's for vertical, but it's when they do that, they add a little bit of this mount material, which you're going to find out it really improves the corrosion aspects. So this MKP, it consists of magnesium oxide, potassium phosphate, calcinated aluminosilicates, graded aggregates, and fibers. And it uses water as an activator. Okay, MKP-VO is really MKP plus that Endure product. So it has the soybean product that tends to block pores and has a tiny bit of MALP in it. Okay. Objective of the study, evaluate the MALP material with and without Endure, study shrinkage, which is a problem for MALP, resistance to freeze-thaw and scaling, degree of protection against corrosion of reinforcing steel. And Dr. Darwin does a crack beam test where the artificial crack goes straight to the rebar. So research.
I think it's my turn.
Yes, sir.
All right, so here's what we did. We did tests for shrinkage, freeze-thaw, scaling, and corrosion. So the shrinkage test is the regular ASTM test for shrinkage, but instead of waiting 28 days to measure the length of the specimen, we measure it right away because you get a lot of volume change and it sets up really, really fast. So we start measuring right away. Here's the results. On the vertical axis, you see the amount of shrinkage. Horizontal axis, you see the age. If there's an increase in shrinkage, if it goes up, that means it's expanding. If it goes down, that means it's shrinking. So green, what is green? Green is the MKP-VO. That's what the MKP with a little extra MALP and a little Endure in it, and it expands. That's the MKP. Without the MALP and the Endure, it expands and then it shrinks a little bit. Well, expanding is good because if you put it in a repair, you want the crack. You don't want a crack to form adjacent to the repair region. The other three materials all shrink, and that means the potential for opening up a crack at the edge of a repair. Okay, we also check freeze-thaw. Now, when we do freeze-thaw, we use the standard ASTM method, C666. It's got two different methods. One you freeze and thaw in water, and the other you freeze in air and thaw in water. We ran both these. We have a limited time to show you what we got, so we'll talk about freezing and thawing in water, which is the worst condition. What you do is you freeze and thaw after so many cycles. You measure the natural frequency of the concrete. The natural frequency helps you determine what the modulus of elasticity is, and the higher the natural frequency, the higher the modulus of elasticity, and the less the damage. If you got damage, you'll see the frequency drop. That then converts to a decrease in how stiff the concrete is, and you get a feeling for what kind of the damage is. So here we started off with three kinds of specimens. One with solid material all the way through, one with conventional concrete at one end, and the phoscrete, which is the trade name of this material, on the other, with a vertical interface, and we also tried it with a horizontal interface. I'm going to show you no results for the one in the middle because it fell apart right away. But we did get good results for the solid material and the solid material in conjunction with conventional concrete. These are the results. Vertical axis is the percentage of the initial modulus of elasticity, and the horizontal axis is how many freeze-thaw cycles. Now, if the modulus of elasticity goes up, that's good. If it drops, that's not good. And so what we see across the top, we see the two different versions of the MALP. The first thing we started evaluating. Remembering MALP shrinks, so that's not so good, but this is freeze-thaw. And what we see here is we see the two different versions of MALP go up. That means they're absorbing some water, actually, even though they're quite dense. And this stays constant. So the key point is that these lines are almost horizontal, meaning no damage from freeze-thaw. Now at the bottom, you see those green circles going down. That's the really good low shrinkage material. Actually, the one that expands, but it does not do well under freeze-thaw cycles. And so that's not good. And in the middle, we have the two cases, the MKPVO that has a little bit of MALP in it and some Endure. And then we have the combination of the MALP and the conventional concrete. Now notice it's that pink line in the middle at 90%, that's the failure level. And if you can get past about 650 cycles, that's a pretty good material, even though it does drop. And so we know we can combine those materials with conventional concrete and do okay. And the MKPVO looks pretty good. All right, we also check scaling. Now, we don't use ASTM because ASTM has thrown out their scaling tests. And there's some good reasons for that, which we could talk about later. But we use the Quebec test, which has been determined to give you a better match with what happens in the field. You pre-saturate the material, you go through under cycles of freezing and thawing, not a lot of them. And what you do is you measure how much material is lost in terms of pounds per square foot. And so here we have the results from the test. The vertical axis is the mass loss in pounds per square foot. The horizontal axis is the number of cycles. You only have to go through 56 cycles on this. What this tells us is, I mean, everything's flipping back and forth. The two upper lines are the two versions of MALP. The ones that did so well in corrosion, they do really bad on the scaling. The ones that are horizontal down near the low end are the ones, especially MKP, did very poorly in the freeze-thaw, but does really well in scaling. And so if those two horizontal lines are the two failure levels for the province of Quebec and the province of Ontario. It doesn't matter what they are. We see that the materials we'd like to use in terms of freeze-thaw are not doing well in terms of scaling. Okay, how about corrosion? Well, we run corrosion tests both indoors and outdoors. These are our corrosion test specimens that we use, one without a crack above the top reinforcing steel, one with a simulated crack 12 mils wide above the top rebar. We pond 15% salt solution on the top, cycle through its cycle wetting and drying, pumps the salt down to the level of the steel, and we measure the corrosion loss that occurs between the top and the bottom bars. And what do we get? Well, vertical axis is the corrosion rate in micrometers per year. And the horizontal axis is the time of weeks for our cycling of wetting and drying. So you see numbers like 15 or 20 micrometers per year. What does that mean? Well, if you have 25 micrometers of loss, you'll crack the concrete. If you got a bridge deck with 25 micrometers, so that's obviously not good. These are the crack specimens, which is not too dissimilar from bridge decks. And we can see it coming across the top is the MKP. It's not doing very well at all, even though it had low shrinkage. The blue line is actually, that's just conventional concrete. We threw that in there to see how it did. So the MKP and conventional concrete look about the same. The red, I guess they're red squares going through there, that's interesting. That's the MKPVO. It starts off very low, then it jumps up looking as bad as the other two, and then it comes back down and does pretty well for the rest of the test, which means there's some potential there. And then we have all the stuff running along at the very bottom with essentially zero corrosion. Those are the two different versions of MALP. And also the MALP with the, in this case, we also combine MALP in the top with conventional concrete below. So we're getting another picture. Okay, how about out in the field? So we also, for the field test, what we call field tests, we cast 4x4 sections that represent bridge decks. The only difference between this and a bridge deck is that we only have 1 inch of cover on top of the top reinforcement instead of 2.5 or 3 inches on top. And then you can see the shaded in areas. We have different kinds of repairs that we put in there, and the repair is in this case would be the MALP material. Okay, so how did it do? Well, again, the vertical axis is corrosion rate, horizontal axis is time in months, and we see two sets of data here. There's two lower sets that were not exactly curves, but there's the results. This is the corrosion rate, and this is for conventional concrete with and without cracks, simulated cracks right over the bars. And that's doing better than the other two, which is actually types of repair with the MALP. And so what's happening here? Well, what's happening is that the MALP shrinks away and gives us a path salt down to the bar. So that means we need to do something if we want to make this a truly great repair material. Okay, but I would emphasize that, as you can see, the rate of corrosion rate in both these cases is much, much slower than what we have in our lab specimens. Oops. Okay, so summarize, in terms of shrinkage, we have the three of the materials, the two versions of MALP and the MKPVO, they shrink. MKPVO somewhat less than the two versions of MALP. MKP by itself expands and then shrinks, but actually the shrinkage rate is slower than it is for the MALP. So it looks like pretty good as far as shrinkage. But in freeze thaw, MKP does not do so well, all right? Whereas MALP does well, MKPVO is kind of in the middle. And then we have scaling. In this case, our great freeze thaw materials do very poorly in scaling, where both versions, our MALP material does poorly, MKP does extremely well. And then in terms of corrosion, well, we flip back again. MALP does well in that, but it's clearly, if a rebar is totally surrounded by MALP, great. If it gives a path for salt to get down to the bar, then not so good. And then MKP and MKPVO are there less effective. Okay, so try to close up the time some.
All right, so let's thank Dr. Darwin for his presentation. We have time for maybe a question, if anybody has one. All right, Shreya, let me come to you.
Thank you for the great presentation. In the graph for corrosion rate with micron per year,
Yeah.
and with respect to the type of coating material or repair material, we saw that the MKP rose a little and then dropped again and stabilized.
One kind. It's the VO,
Right.
it's the VO that has a little MALP and a little Endure in it.
Right. So I was curious, do you think when it rises and then comes back down, the crack is somewhat sealing because it opened up and then started going back?
No, I think it's what protects material with MALP, and also I think with this MKPVO, is the fact that the material is so dense, and it limits the amount of oxygen, moisture, and salt that can get down there. Even if with a crack, you got to have oxygen and moisture to the lower bars that act as a cathode, and if you don't have any oxygen and moisture, you get no macro cell corrosion. So that's the main reason.
I see.
I think that's it.
Thank you so much.
All right, thank you, Dr. Darwin. Thank you, Walt. Hold that question till the end. We're running behind on time just a little bit. If we get done early, we'll have time for questions for all of our speakers. Also, look for them in the break afterward as well. So our next presentation is again a joint presentation with Dr. Joshua Lee, who's a professor of civil and environmental engineering at Oklahoma State University, and Mr. Walt Peters is with us again. They're going to be talking about a bridge impact study. Dr. Lee has expertise in a lot of different areas of transportation engineering. He's done a lot of work within Oklahoma over the years, federally funded, et cetera. You can, again, take a look at his bio in the program. So I'll let y'all take it away.
All right. Presentation number 2. Okay. Dr. Lee's team included himself, Conram Parajuli, close, I hope, and Dr. Bruce Russell. Dr. Russell couldn't be with us today, but it's a great team that he put together, and I think they did some really great work. And we got out on our highways, got some help from ODOT, and he did a lot of work with his students where we used the instrumentation, and we used some weigh in motion, and we were able to get at these impact factors. So I'm going to have to get a lot closer. Um, so we're going to talk about dynamic impact. It's when you design a bridge, RFD, you say it's going to be 33%, period. So that's the way our spec's written. Older specs, the span length got to be a factor, and it was a simple formula to follow. But when we do load rating, there is some provision in some of the, well, our MBE addresses it in not the main part, but in the, well, I'm not thinking of the right word, but sorry. Anyway, this is, we're going to be studying the impact factor, and really he starts saying key influencing factors there, and he talks about the deck roughness. So when we think about that, we start thinking about the IRI, which stands for the International Roughness Index, which he's doing this at 60 miles per hour. He's got this vehicle with some lasers on it, and he's collecting this, and he did a big section of I-35, and he's also done some on I-40. So, I mean, this is a tremendous effort. And so we want to create a method at getting our impact factors that's cost effective, build a practical data-driven models, develop faster, accurate methods, and maintain a priority by correlating. You have these rough approach slabs that are really the bump at the end of the bridge it's not just hard on your car on its shock absorbers, it's hard on our bridges. So if Dr. Lee finds some of these approach slabs that are not too smooth, that's a good candidate for us to do some maintenance on. Okay. Any research project you do is going to have a literature review, and this is pretty important because you kind of see what's been done by other professors, and you get an idea of what you need for sensors, for what really causes the impact, and it can be a lot of different things. It's the weight of the truck and the speed that the vehicle's going, alternative data, approaches, that there's different techniques that you can use, and processing the information can be kind of a challenge because we look at 13 bridges and we get all kinds of data on all kinds of different types of bridges, which includes concrete, steel, pre-stressed, simple, continuous. We even had one bridge that was a rigid frame, which kind of surprised me. The pier cap was kind of built into the superstructure. So when you drive over the bridge, you actually get a little stress in the column. Approach conditions, he went to the extremes. You know, I think in terms of good, fair, poor, he thinks he wants to do the really good bridge decks and he wants to do the really poor bridge decks. So that gives him better data to evaluate how the bridges are performing. The traffic conditions, you know, we did one bridge, a few bridges on 183 south of Clinton. Things, very little traffic. Then we get on I-35 and the traffic's almost overwhelming. You get the number of trucks you want pretty quickly. Ease of instrumentation. Dr. Lee did a tremendous job of finding a way to do weigh in motion, kind of up front of the bridge and then on the bridge deck to get the static and the dynamic influences. Okay, now we're going to look at the different bridge locations. We had some on I-35, north and south, and we had some south of Clinton on 183, and we had different types. There was some that was continuous for live load and others that had different problems, so, or different construction.
Thank you all. So after we select the bridges, a few instruments has been used for the field data collection. So we draw like some kind of cartoon right here. So we have wave motion. On the surface, we have vehicles to test the distresses and also the profiles of the roadway and also the bridge deck. At the same time, we have the cameras because we have all type of traffic on the road. So you may have multiple vehicles on the road. So we are able to use the camera so that we know whether there's only one vehicle or there's multiple vehicles because some of the impacts will be combined. We also use Surpro, so it's in the small instrument next room. We have the small instrument right here. So this is a ground truth profiling device. Under the bridge, we have the strain gauge and also the IMU. So we have two sets of weight in motion sensor. The original idea is we place one weight in motion on the roadway to simulate the static load, and another one on the bridge deck, the first middle span, to simulate the dynamic load. At the same time, our strain gauge and accelerometer IMU was right below the middle span. The cameras is trying to track the torque event, when is the torque, in which lane, and also what type of torque, and so on. So that we are able to, based on the video data, to exclude the data that with multiple vehicles on the deck. So we want to have a clean signal, so with one torque on the deck. And Surpro, we use this to get the profiles based on the literature review. So the profiles are one of the most important parameters that impact the dynamic factor. So we want to have a very accurate profiles. As we know, a lot of the times for the roadway, we use the accelerometer-based profiler. Profile, as we know, a vehicle, you have the suspension. When you have the accelerometer in the vehicle, if the road is bumpy, there are two types of responses. One is from the vehicle, the other one is from the road itself. So this one is based on in kilometer. So there are two wheels. We know the distance of the two wheels, and using kilometer, you measure the angle. So therefore, you are able to know the height difference, the change. So this one essentially is a true profile. And the bridge instrumentation, we have the strain gauges and also the IMU. So if the single span is at the bottom flange of the girder or near the middle span, for the multiple span, we only work on the first span. We also use the vehicle in the front. You can see this are the AIMS profiler, the longitudinal profiler. And also in the back of the vehicle, that was to acquire the surface distress condition. Here are some of the data we have. For example, we have the 2D and the 3D. We have the cracks. We have all type of distresses. At the same time, the figure below is the RRI, the longitudinal profiles. So for the roadway design, for the roadway, the PMS, generally we use 25 feet or 50 feet, the wavelength, to get our RRI in order to quantify our roughness. But for the bridge, in order to identify the bumps and also the irregularity on the bridge deck, we use 1 feet. So that some of the numbers, RRI, is really big. In roadway, generally we probably, on 35, we had 120, 130. So that probably pretty not very good condition. But for the bridge deck, if you use 1 feet, it can go 1,200, 2,000 inch per mile. So we use that to identify the bumps and also some of the distresses on the road. So after we have all the field data, so we compile the 3 different types of data. One is the bridge data. The bridge data is primarily from the NBI and also from ODOT. So we have some of the geometry and what type of the bridges and so on. And the second type is the surface condition, including the roadway and also the bridge deck. There are primarily 2 types of data. One is the distresses, including the cracks and all the different the bumps and so on. And based on the profile data, we get the roughness data at 1 feet per mile, 1 feet interval. So we also was able to identify the bumps. These are the surface condition data. The third part is the impact factor, the calculation. Because the data was pretty noisy, so then the first thing we need to do the filtering, the denoising. Denoising, as we know, for the signal is a time domain signal, and we transfer into a frequency domain so that we know which part of the major frequency, so we can call it like the low frequency and the high frequency. So we use the power spectral density, so that was widely used in roadway. So we use that to understand the frequency, the energy of your signal. So then we apply the Baldworth or low pass filter to denoise the data. After that, we use this one, the figure showed right here. So the real data is a dynamic signal, and we use a filtering approach to smooth our signal, and so that we are able to estimate the static strain. So we have the dynamic strain and the static strain, then we are able to compute the impact factor. So that approach has been used by a few state DOT. So the most closest one is by Iowa DOT. After we have that, so this is the major challenge, because on 35 we can have thousands of vehicles per hour. So there's a lot of vehicles. Some of them have different types. So therefore, in order to make this kind of data processing feasible, we developed a software. So this software, you can see the picture right there is a video camera. And then you have here, this is the strain gauge, and this is the IMU. And here you have all different kind of tools to help us to sync the data, because all the sensors are using different computers. The IMU, when you motion is before the roadway and on the bridge deck, and the strain gauge is below the bridge, and there's 3-4 computers at the same time. So we want to sync that. So then we have different tools right here, and this one will be the way in motion. So we use this software to sync the data, and also at the same time use the software to automatically calculate all these different numbers. So this is the previous one is a closed loop, and this one is like, for example, it's an hour. So you will see how many vehicles, each of the spikes of vehicle, you got some bigger ones, you got smaller ones, and also this way in motion and this IMU data. Okay, after we have that, Dr. Manina, could you click on the video? So we made a very short 30-second video. So this is you can see the trucks passing by, and each of the truck you see of the strain gauge and IMU and also the way in motion. Everything has been synced. And the software is able to calculate all the parameters and save into a database. So then after that, we will use the data for our model development, because our goal is to develop a procedure to estimate my impact factor. Okay. So the model, we have two types. One is the regression model, one is using machine learning. So of course, the dependent variable will be our impact factor. Our some independent variable will be the 3 types: the bridge, the roadway condition, and the vehicle. Here's a regression model. So most of you are very familiar with the regression model. So here shows some of the results, which ones are most significant. So here, generally speaking, so we have the most significant variable are the roughness, the skew angle, and also the vehicle speed. That can increase our impact factor. But as we know, the regression models, one of the assumptions is the relationship are linear, between y and x are linear. So then we use some nonlinear. We also tried multiple machine learning models. So this one is from the random forest. Random forest, you can see right here, this is the feature importance. So the longer the bar, the most important is the parameter. So you can see right here. So here has the RRI at the deck. So the variance of the RRI on the deck. And also you have the weight of the vehicle speed, and some of the wheelbase, the length, and the deck type, and some of those, you can see most significant variables kind of make sense. And how we can use that. So here are some of the validation. So you can see the regression model. So the variance is much larger, the band is larger, and the random forest, so the results are a little bit better. Okay, how we are going to use that? Because right now, our roadway, the PMS, we collect the data every year on the national highway systems. We have the roughness data. But generally for the pavement design, pavement PMS, we exclude the bridge data from the PMS. So the data we collected, but right now we don't use it. So in this model, previous the model developed, so we are able to use our roughness, and we are also able to characterize, use our vehicle, the loading conditions. Just like Dr. Lei just mentioned, we don't care whether it's 82 kips or 80 kips. So we use fully loaded, empty loaded, or partially loaded. We put it into the equation, and then the speed and so on. So we are able to estimate the impact factor. So this is a bridge close to Purcell on the Interstate 35.
I think what's interesting about that slide was that the heavier weight, the heavier gross weight, actually had lower impact, which for load rating, I think that's something you want to hear. The higher speeds did cause greater impact, so that's a concern. All right, summary. So Dr. Lee and his team has done a phenomenal job, I think, of developing a rapid method to estimate bridge impact factors, which I think could be used for load rating. I think just in a few years that'll may be happening. We'll go through the Committee on Bridges and Structures and see if we can make that happen. We've collected and synchronized some multi-sensor data. We've used smoothing techniques, which was amazing. That machine learning is just something that really neat stuff. So he developed some very predictive models. The future work is going to expand the data sets and apply advanced methods for improved model accuracy. So maybe those R-square values will get I think 90s is too optimistic, but I think there's going to be some improvement.
All right, thank you, Walt and Dr. Lee. I think we have time for one question. Anybody has one? All right, so I'll ask a question. Walt, how long do you think that it would take to get this to where it's going to be usable for load rating in terms of getting it through the committees, and how comfortable would you be using it even right now?
I think we need to do some more work before we get it into AASHTO, like the MBE, Manual on Bridge Evaluation, which we're in the process of rewriting that, and I think I kind of want to make an effort at that. But I think we're still a few years off, and bridge engineers tend to be very, very conservative. So they may want to stay with 33% or something like that, just because they don't want to take chances or something like that. So, and we have corrosion issues that are hard to evaluate sometimes. So, but if nothing else, I think we can identify locations where we got a rough ride that by doing a little maintenance, we could get our impact factors down and actually improve the load rating of our bridges, whether we take advantage of it or not.
Okay.
Yeah, I had a few sentences right here, and thank you all. And so right now we instrument 13 bridges, and there's one in State Highway 182, 83. So that one with quite not too many trucks, but most of them on 35. 35, I think most of the trucks, generally there's a lot of them fully loaded, and the loading spectrum is not that representative. And also the speed on the 35, generally you got a 70 to 80. There's nobody around 50 or 60. Most of them 70, 75. And the speed range is pretty low. It's pretty small. So I think when you have a higher speed, your impact factor is higher. And Walt just mentioned when the vehicle is, the load is heavier load. So generally when we drive, if it's a lighter torque, lighter load, the vehicle jumps higher, right? So that is kind of makes sense, and the impact factor with the lighter torques, and generally the IR will go up a little bit. IM will go up a little bit. I think we need more samples.
Okay, well, let's thank our speakers. And ask our last speaker to come forward. We have Dr. Syed Ashiq Ali, who's going to be presenting on rapid assessment of network-level pavement conditions using novel tools. Dr. Ali is our newest assistant professor in the School of Civil Engineering and Environmental Science at the University of Oklahoma. He is a key team member as part of the Southern Plains Transportation Center, and he has worked on several projects related to pavements and other types of materials in Oklahoma.
Thank you very much, Dr. Floyd. It's nice to be here, and I'm apologizing before because I'm standing between you and your lunch, so please forgive me and be patient with me. The time we have, I think we are running a little short on time, so I'll try to give you an overview, but also at the same time, I may have to skip a few slides, so I apologize for that before. So my topic today is rapid assessment of network-level pavement conditions using novel tools. So here in this project, actually, we tried to use different tools that are available for pavement condition assessment, both on the structural side and also on the functional or surface condition side as well. And we tried to use some in-house tools. Also, we tried to use some extensive tools that is not available in the market right now. So, before I start, I want to acknowledge the Southern Plains Transportation Center for supporting this study, Oklahoma Department of Transportation for helping with all the logistics from data collection to supporting and other stuffs. Matthias Mendez, I have to mention that name because he was the one, he started this work, and then Shagor Ghosh, Meherun Nisa, they continued this work. Without our students, we will not be able to do our work, right? Members of the OU research team, Dr. Lee and his research team, OSU was a part of this project as well. TTI team as well, they helped us a lot on the data collection and also on the analysis. And Odor District 4 for helping us with core collection and others. In an overall, nationwide, we have a relatively bad pavement rating. It came out as D in the 2021 ASC report card. So that's not very good. So that indicates that our pavement needs repair, some rehabilitation work, right? So conventional test that we are doing right now is relatively time consuming, and they're expensive and requires lane closures, and we are also putting our staff on the road, so this is not very safe as well. So what we are doing, what we need to expedite the process. We need something that is fast, that is less expensive, and also to collect lots of data, give us lots of information in short amount of time. So that's why the topic says that it is a rapid assessment. We're trying to do something rapid. Currently, the way we do the structural evaluation of pavement is using falling weight deflectometer. Falling weight deflectometer has been used for several decades now, and it is a very reliable tool, very highly accurate. But the problem with falling weight deflectometer is that you have to close the lane, you have to put your crew on the pavement, or also at the same time you need traffic control. Okay? And also you are limited on the data. You cannot collect continuous data. It is a spot test. You take maybe every 10th of a mile, take results, and you cannot do it every year. Generally, they do it for every 2 years or so. So this is not a very frequent data collection as well. But this is a very good tool, very reliable tool. PAVE 3D 8K, so what we wanted to see, what are the other things that we can explore? So Dr. Lee and his team already has worked on PAVE 3D 8K. It is a very good tool. It has already been proven to be a good tool for pavement condition assessment. at a very high resolution. It can give you transverse and longitudinal profiles. So and it has been used by, for quite some time now. So Dr. Lee, I'm preaching for you here. Please send some money to my account, please. So we also wanted to see what other methods are available, tools are available for pavement condition assessment. At TTI, they have developed one tool. This is called air-coupled ground penetrating radar, or GPR. This is a 1 gigahertz air-coupled GPR that can run at traffic speed. So you do not have to close the lane. Okay? And the good thing about GPR is that it doesn't only look at the top, it can look at what is going on underneath, on the subsurface condition as well. So that's a very good thing. And it can run at 60 to 70 miles per hour. There is no need for traffic control. And it provides pavement structurals. It shows you what are the anomalies underneath the pavement. So that's very, very good information to get. Okay. Okay. So then the next tool that I'm going to introduce you is called the traffic speed deflectometer. So who has not heard about the traffic speed deflectometer here? Or who does know about traffic speed deflectometer? Anyone? Okay, so I can see a few hands. So this is a new tool. This is relatively new tool. It has been in the market for maybe 4 or 5 years now. We have only one TSD truck in USA, only one. Okay, that is run by ARRB, and generally right now they are collecting some basic data. The traffic speed deflectometer can do the work similar to falling weight deflectometer, but this is continuous. This truck runs at highway speed. You do not need to lane closure. You do not need any traffic control or anything. It will run. It will just collect the data by putting some load on the wheel, right? It is putting load through the wheel on the rear wheel, right rear wheel, and then at the same time, it is collecting the deflection data using laser, okay? And it can collect the whole I-35 data in one day. And they did it here. So traffic speed deflector is a new thing. This is coming up very fast, very safe, and give you a lot of data in a relatively small amount of time. So at high measurement speed, dynamic loading is more representative of what traffic loading is actually happening. And this is a very good tool for network level assessment, right? If you want to assess the whole network, this is kind of tool you need where you can take lots of data within a short period of time. And from what we get from this is the truck you can see. From the traffic speed deflectometer, what we get is a deflection bowl. Because of the wheel load we are applying, we get a deflection bowl. And by analyzing that deflection bowl, we can actually determine what is the condition of the pavement. Okay? That's the ultimate goal. And I'm going to show you there are several parameters that has been proposed to use as a tool for classifying whether your pavement is good, bad, poor. But I'm going to show some of the parameters as well. So the objective of this study was to look at what are the in-house technology that we have, and let's compare them with the traffic speed deflectometer and other data that we can get. And also at the same time, we want to see how we can use this tool, how we can use this data to develop or refine the network level pavement condition rating system, okay? Which is generally, if you look at the federal highway requirement, they generally classify into 3 categories: good, fair, poor, right? So we wanted to see how or what are the threshold value for good, fair, poor based on TSD or other parameters that we have. So ultimate goal right now, federal highway requirement is generally going with the surface condition. They look at the surface condition and whether we have met it or not, that actually used in the pavement management system. But the ultimate goal is to let's look at whether we can include the structural condition as an input to, in the pavement management system so that we can at the same time use that for the federal reporting and also use it as a more data-informed way of defining our maintenance and other activities as well. All right, so this is the methodology. I'm not going to go over this. That we collected TSD data first, and from that TSD data, we try to define few parameters from the TSD to find out good, fair, and poor. And then from that, we selected some study location. On those study locations, we collected data on GPR, we collected data on fast falling weight deflectometer, which is almost similar to falling weight deflectometer, but it also runs a little bit faster than falling weight deflectometer. We took help from TTI to do that. We also collected data with PF3D8K, and we analyzed that data, try to find out the correlation between different parameters that we can get from all these different technologies. And then at the end, we try to come up with refine the TSD threshold values. So this is just data collection. ARRB helped us with data collection, and that data collection was done in October 2022. We saw that like we needed raw data for more analysis. They helped us with that raw data. Data was collected on I-35 southbound, I-40 eastbound, and I-40 westbound, the whole sections, and relatively very small amount of time. Within 2 days, actually, they were able to collect a lot of data. Then PF3D8K was done by Dr. Lee's group in the summer of 2024, and then raw data was processed and analyzed by his team and sent to us for more analysis. Falling weight deflectometer and GPR was done almost at the same time in the summer of 2024 by the TTI crew. And also in the summer, during that summer, we also collected some core to look at what is the actual pavement condition. We collected some core, selectively core from distressed and non-distressed location to see whether actually what we are getting from TSD and other technology, are they saying the same thing or not? All right, so I have to point it that way. All right, so from TSD data, so this is a massive amount of data we have received from TSD. So after getting that data, what we had to do, we had to clean the data. There are lots of anomaly in the data, so we have to clean it. We have to take out the breeze from the data because we are just looking at the pavement condition, not on the breeze condition. So we have to take out the breeze data. We had to clean a lot of it. And then after that, we analyzed and developed several parameters. The first parameter is the SCI 300. This is called the surface curvature index. This is developed from the TSD, which is actually the deflection at 0, that means underneath the wheel, and also deflection at 300 millimeter from the wheel. So this is based on that parameter. We have developed this SCI 300 was calculated, and this parameter is actually known to be very good, has very good correlation with the surface structural condition. So we plan to use that, and this is the initially, so Oklahoma DOT does not, right now we do not have any threshold limits to define the pavement as good, fair, poor. So what we did, we tried to look at the literature, find out which state agency or literature has a requirement, SCI requirement. So we found that the Virginia Tech Institute, they have proposed a requirement for SCI 300, and we use that requirement. As a less than 68.58 will be a good condition, between 68.58 to 93.98 will be a fair, and more than 93.58 will be considered as a poor pavement. We found most of the pavement was in a very good condition, because this is an interstate. We were expecting very low deflection on it. So we found that some places we have seen some higher deflection. Those are actually, so whenever we see some deflection, we went there. There was a video included with the TSD data. And we have seen that location is actually, there is a problem between, some of those locations has some problem between the shoulder and mainline joint. There was some like a joint failure over there. Other than that, the pavement looks very good. So this is the data for I-35, I-40 westbound, I-40 eastbound, based on SCI 300. We calculated another parameter. This is called BCI, Base Curvature Index, which is a representative of more on subgrade or subsurface condition of the pavement. So these are the this is some of the threshold value we use from Text DOT, and we have seen that almost all the pavement have shown very good results actually. So both I-35 and I-40 is in very good condition in those locations. We also wanted to see if there is any other parameter that could be of help to define the threshold. AUPP, area under the pavement profile, there is another parameter we wanted to see. Although there is currently no limit or threshold available for that, but we wanted to use it for our analysis. So based on all this, what we did, we tried to find out some locations that we can do for further study. We have selected 3 sections from I-40, 3 sections from I-35, and so and classify them as fair, good, and poor. But remember, this is not based. This classification is based on the initial data that we have. This is not a final classification. And so, and what we did, we collected more data. We collected the PF3D 8K data, fast falling wave deflectometer data, and also we did some coding on those specific locations. And so what we can see from PF3D 8K, this section 2 was considered as good. This is a result from the I-35. So section 2 was considered as good. Just look at the rod depth from the PF3D 8K. Very low rod depth. So that also actually shows that the PF3, whatever we are getting from PF3D 8K is actually telling the same thing from the TSD as well. Section 1, fair, it has a little bit higher rod depth, but not much. Poor section, it has some spikes, but not that much. Okay, so still very good correlation between the PF3D 8K and TSD. Coding, so we wanted to see the coding, how does the course looks like, or the actual pavement condition is. So we took some core from the I-35 sections, and we have seen that like section 2, which is good, it is actually a composite section, right? So composite section with concrete on the top and asphalt on the base, and it shows actually very good, very low deflection and very good condition. Section 1, which is fair, has a very thicker pavement with asphalt stabilized base. And section 3, which is poor, so we have seen some delamination on that. We were not able to take out the full core because like the bottom part kind of fall apart. So, so this is the condition. And also I-40 sections, we have seen that I-40 section is generally a flexible pavement with a thickness of around 10 inch to more than 10 inch thickness. Okay? So we also, as I mentioned, we did the fast falling wave deflectometer to find out whether the falling wave deflectometer data correlate with the TSD data or not. So TSD shows like the section 2, which is good, very low deflection. Section 2 and the other sections, fair and poor, also shows not that bad, but like almost similar results. From GPR, we collected the GPR data on all those sections and tried to find out, like, compare point to point. Also, we have found that it also tells us the same thing. The good sections did not show much anomaly on the GPR data. The fair section has some points where we may have some problem on the subsurface, and the poor section has shown a little bit higher amount of anomaly on the GPR readings. But we were not able to correlate directly GPR data with the TSD data because GPR data is formatted in a different way than the TSD. So formatting wise, it was a nightmare to compare between them two. On the I-40 section, I-40 section, we have seen the same thing too. So based on that, we tried to find out the how different technologies compare using some AI tool with different AI model. We tried to compare between for example, TSD has different parameters, SCI 300, BCI, and other parameters. We tried to compare between this TSD, FWD, PF3D 8K parameters. And we have found very good correlations, and this is just a table that shows which model was used and which parameter correlate well with the FWD. So if we in this study, we kind of compare FWD as the basis or the reference parameter. So FWD W1 has shown very good correlation with SCI 300 and AUPP and D1500 and some other parameters too, some other combination as well. So using that information and considering FWD as a reference, we try to calculate the remaining life of the pavement. Okay? And from that remaining life of the pavement that we collected data from, and we tried to correlate that remaining life with the TSD SCI 300 parameter, as it has shown very good correlation with other parameters. So from that, we have developed this equation where the SCI 300 is correlated with the remaining life of the both I-35 and I-40 pavement. Okay? And using that, we actually use this information to come up with a pavement threshold for both I-35 and I-40. And these are the threshold. We have considered that, generally it is considered that if the pavement has a remaining life of less than 2 years, it is considered poor. Remaining life of 2 to 5 years is generally fair. More than 5 years is generally considered as a good pavement. So based on the equation or based on the correlation we developed in our last slide, we found out the traffic threshold that is representative of each of these parameter and what is the SCI 300 value for that. And we have seen that the parameter, there is some changes on all these parameters that was required and to correlate for the Oklahoma, to accommodate the Oklahoma condition. And so this is the, on the top we have I-35, on the bottom we have I-40. And so with that I will stop my slide. So we have seen that TSD could be used and as a tool for rapid assessment on the network level. And we have found very good correlation between different technologies, so they can be used alternatively. And we have defined some threshold that also may need some refinement with when we go for more data collection. With that, thank you very much.
All right, thank you, Dr. Ali, for making up some time for us. Thanks for the great presentation. We have time, we can take a question or so before we go on to lunch. Note that you are the person between us and lunch, but any questions? Yes, Dr. Alkashah.
Thank you, Dr. Ashik. Nice presentation. So what does it mean that you have different thresholds for ranking the pavements based on the pavement itself? So you had 2 different sections, and then you developed 2 different thresholds for one for each pavement. So,
yes, thank you very much for that point. So we have analyzed I-35 and I-40 separately. As you can see, I-35, when we were analyzing together, there was some problem. I-35 has many sections with composite pavement, and I-40 has flexible pavement. So when we are analyzing the data, we have seen that if we try to compare between, combine them two, it kind of give us some discrete results. It was very difficult to compare between them. So we started treating those 2 as separately. But at the end, what we have not shown it here, but our idea is to now let's look at it together, I-35 and I-40, and see whether we can come up with one single threshold value. That will be the next step that we can use for both Oklahoma, anywhere in Oklahoma. Thank you.
All right, well, let's thank our speakers one more time. All right, now we're going to go on to lunch. We also have the posters for viewing across the hall, the demos next door. I think 3 of the speakers from this session have demos, so please go by, check those out, talk to our speakers, ask them the questions you didn't get to ask in here. Thank you all for attending. Enjoy your lunch, and we'll be back at 1:15.